All right, Dr. Matthew Mitchell, thanks for joining me today.
Please, Dr. Matthew Mitchell was my father.
Well, I have to say, first of all, congratulations. You just defended your dissertation in
Yeah.
mathematics at the University of Michigan.
Well, it
Well,
was in physics,
it wasn't
technically. Yeah.
yeah, okay, so it was still in physics.
It
Okay, I
was
was
still in
going to say,
physics.
it's a bit funny because we started off together in the program as PhD students in physics,
That's
and then
right.
somehow you went to the dark side and you started going across the hall to, or across the road, I should say, to the
Yeah.
math department.
Right.
So tell me how that happened. How did you just leave us like that?
Well, yeah. So we shared an office together, and despite us sharing QFT and everything, never wanted to do homework with me. That's fine though.
Let the record show that it's false.
I wanted to do homework at the opportune hour of 11 p.m. and Ibrahim was not all right with that.
I like to
So
sleep.
yeah, I started in high energy physics um, at University of Michigan. I during the pandemic basically is when I decided that I had a lot of time to myself and a lot of time to think about exactly what it was that I liked in physics and mathematics. And I decided that high energy physics wasn't exactly it. That it was more kind of like fluid dynamics, partial differential equation kind of stuff that I was more interested in. And so I eventually meandered my way as I was taking some courses in the math department to be the PhD student of one Peter Miller at the University of Michigan, who's he's really well known in his field um, of this like partial differential equations, kind of fluid dynamic adjacent. I didn't end up doing exactly fluid dynamics, but it's sort of adjacent to that, the mathematical side, sort of. Um, yeah, and I just as like pretty much his pitch to me on what the what project he had in mind for me like immediately solidified, oh yeah, this is exactly what I want to do. Because it was a very interesting mathematical field, this field of solitons. It has this weird connection between fluid dynamics and the Schrodinger equation, which governs quantum mechanics. And I just found it so fascinating. Immediately, I was like, "Oh yeah, this is exactly what I want to do."
So
So
were
then
you
I,
always interested from, let's say, undergrad in sort of these ideas of partial differential equations and fluid dynamics, or did that develop mainly in graduate school?
Yeah, it was more like I always enjoyed partial differential equations, fluid dynamics kind of stuff. Um, but I was more in undergrad. I want to be doing the big things. I want to be doing like uh, this. All of this mathematics is related to like quantum field theory and stuff like that. So I want to be doing the big stuff. I want to be doing QFT, high energy theory, string theory, kind of related stuff. And then when I finally got to like see all of that stuff for the first time in graduate school, I was like, oh yeah, it's not it's interesting, but it's not exactly what I want to be doing. So yeah, so that's when I went back to my roots. In undergrad, I took a continuum mechanics course, which is actually the first time I was introduced to something we'll talk about in a little bit, the FPUT or FPUT problem. And the and yeah, and then getting to revisit that and like see it from a different perspective in graduate school was really cool too. So yeah, I felt like I
Nice. Yeah,
was
you,
going.
you mentioned you took a couple of courses in the math department in graduate school. Could you just tell us what those courses were?
Yeah, so I first took a intro to PDEs course because that's we had to do a cognate for our PhD, and even though math is so related to physics, it still counted as a cognate course. So I decided to do a PDEs course, and I was like, oh yeah, this is the stuff I really like. Then the pandemic hit, and I was like, and that's when I started wondering like, oh, what else could I do in graduate school, and that's when I took a course from Peter Miller and we got to talking and I was like, oh yeah, this stuff is actually super interesting.
And so that was the beginning of the dark side.
Yeah, that was the beginning of
Okay,
the dark
so
side.
PDEs, partial differential equations. What is that?
So partial differential equations are specific types of equations. So maybe we take a step back and just think about like equations in general. What's like the first kind of equation that pops into your mind? It might be something like an algebraic equation. Um, the like a basic example of an algebraic equation would be like a quadratic, right? In two variables. So you have like an x and a y, and there's like a quadratic in the x variable, and it's equal to y or something like that. And the solution is like is this function. You could write y as a function of x or something like that. You could plot it. You get this nice shape of a parabola. That's all well and good. Kind of one step up from that would be what we might call an ordinary differential equation. To distinguish it from a partial differential equation, we call it ordinary. And that means it's a differential equation in one variable. What do I mean by a differential equation? That would be an equation that relates a function to one or multiple of its derivatives. So kind of the basic example of a differential equation would be like the derivative of a function is equal to the function itself, right? The if anyone in the audience has taken even a first calculus course, they know about derivatives and they know a function. They probably know a function that is equal to its own derivative, and that would be e to the x, right? The exponential function.
Yeah.
Yeah. But in fact, there's a whole family of functions that have this property, and it's just taking that exponential function and multiplying it by some arbitrary constant, right? So if you have 2 e to the x, if you take its derivative, you'll also get 2 e to the x. And so it's also equal to its own derivative, pi e to the x. You could put any constant in front there and it'll work. So when you have a differential equation, if that's all you have, you get a family of functions as solutions. And if you want to fix one particular function as a solution, you need to provide an initial condition, is what it's usually called, which is just that at some point we know the function takes some value. So at 0, it takes the value of 1. Then we can fix that arbitrary constant out front to be 1 in that case, because e to the x is 1 at 0.
So out of the family of all those solutions, if I have some initial data that helps me choose which one is appropriate for the setting.
Yeah, that's exactly right. So oftentimes ordinary differential equations you're provided the equation itself, but you're also given another piece of information, that initial condition, which helps you fix the solution to be one function, right? Okay, so now let's abstract up one more level and talk about partial differential equations. So these are differential equations where the function has more than one variable. So when a function has more than one variable, you can take a derivative on any one of its variables. And we call those partial derivatives to distinguish them from the fact that the function is not just of one variable and it's totally described by its derivative. It's one derivative, right? There's multiple derivatives. So if you only have one derivative, you only have a partial of the information. You only have the amount of information to describe the function. So I guess that's why it's called a partial derivative. I don't really know what the
So if I'm going northeast, I can ask how fast am I going in the east direction, or how fast am I going in the north?
Yeah. If you want to think of derivatives as rate of changes like that, yeah. If you describe information about how fast you're going east, you don't have information about how fast you're going north. You would need also that information in order to describe your motion totally. Partial differential equations are differential equations where the functions have multiple variables, and so you might have different derivatives. Kind of the basic example is a function that is a function of two variables, one that we call space and one that we call time, right? And so that would be it. And then if we had a differential equation that related the space and time derivatives, that would be a partial differential equation.
And so what's an example of a partial differential equation?
That's a great question. So super common examples that come from undergraduate physics. In fact, I was thinking about it earlier. So much of undergraduate physics is really just PDEs, solving partial differential equations. One that is really basic, but sometimes it shows up in a statistical mechanics or thermodynamics course, would be the heat or diffusion equation, which describes a diffusion of heat through some medium. So as an example, if you take a metal rod and you suspend it over a fire in the middle, and you start heating the metal rod in the middle, but you leave the ends unexposed to the fire, you'll get a temperature profile on the rod where there's high temperature in the middle, and as you go out towards the ends, it's low temperature. You can describe that with a function of the spatial coordinate along the rod, right?
And what about the time coordinate here?
In the time coordinate, the heat equation would tell you how that temperature profile changes in time. So if you know that initial temperature profile, you can use the heat equation to tell you what the temperature profile looks like at some later time. So in that case, there's two spatial derivatives related to one time derivative. That's just the nature of that equation. You can go look it up on Wikipedia, the heat equation, if you want to know the exact equation. So this is how this goes. generally. And like I said there, the initial condition in this case is usually a function of one variable, and you ask how that initial condition results in a solution that changes in the other variable. Um,
Typically, we also hear of boundary conditions. What's the difference between a boundary condition and an initial condition?
yeah, that's a great point. So the boundary conditions, if you have our rod is finite in this example, right? Our rod is finite, and so we have to prescribe the derivatives aren't well defined at the ends because you only have information from one side. So you have to usually prescribe in that case what's happening at the endpoints. In this case, they're exposed to the temperature of the air. So the temperature at the endpoints would be fixed to whatever the temperature is of the air. And so that would be in the mathematics, it becomes conditions on the values of the function at the two endpoints. And that's why we call them boundary conditions, because they're at the boundary of our domain of interest, which is the rod in this case. Yeah, so some other common examples would be the wave equation, which is an equation that describes small perturbations in elastic medium. You can think of that as like vibrations on a guitar string. If you pluck the guitar string in a certain place, when you're holding it back right before you let go, you've provided an initial condition that is the displacement of that string. And as you let it go, it will evolve under the wave equation, and that'll tell you how the string vibrates and how you generate the sound that you hear when a guitar is strummed, right? So in that case, it's actually two spatial derivatives and two time derivatives that are related to each other. And in that case, also the boundary conditions would be fixed. There are other different types of boundary conditions, though. It could be that the derivatives at the ends are set to zero, or we could say if we had a string that was connected at the ends, we can set the value at one end to the value at the other, and it would be some continuum boundary conditions that it actually lives on a loop or something like that.
So there's sort of periodicity happening there.
Yeah, yeah. Often you call those periodic boundary conditions because you require that at one end it's equal to the other, and then you think of it as being on a circle, and it has to then be periodic.
So taking that
Period
example of the
circle.
wave equation, when I teach introductory physics, I usually have an example of a guitar string, and I tell them that one can excite different harmonics on the guitar string. And typically, what I show them is that it's a sum of the harmonics that ends up being displayed on the guitar string and not one harmonic. And somehow you can add together different harmonics and get a final shape on the guitar string. Why does that work for a guitar string? How can
Yeah,
I just
so
add up together harmonics and I get the right answer?
that is an incredible question because all these equations, both the heat equation and the wave equation that we've talked about so far, are examples of linear partial differential equations. And linear just means that there's only ever sort of one function that shows up in a term. It's a sum of a couple terms, and one function, it might show up with some derivatives, but it's only one function there. And this means that if I take two separate solutions that I have found individually to the partial differential equation, I can take their sum and I can show that because derivatives split over sums and the equation is itself a sum of some derivatives of the function, that the sum of the solutions separately is also a solution, right? So in the case of these harmonics, oftentimes what we want to do is decompose some complicated initial condition into some simpler ones that we might have a way of solving the time dynamics for. And then if we take those solutions and add them back up, they solve the complicated initial condition evolved through time under the partial differential equation.
Okay. So when I read your thesis, I saw the term nonlinear partial differential equation. And that's not what you just spoke about right now. You talked about linear differential equations. What I want to get to eventually is what's the difference between linear and nonlinear and how that manifests in these equations. But before that, something you start with in your thesis is a little cute anecdote about John Russell observing something moving. And I just want you to tell us what was that anecdote? How did John Russell, what did he stumble upon?
Yeah, so John Scott Russell was a Scottish scientist in the 1800s, and he opens up what he a paper that he wrote to the British Association for the Advancement of Science called the Report on Waves with this very enthralling description of him chasing a wave that's propagating down a canal on horseback for several miles. And the reason he's doing this is because he knows that the zeitgeist of the time was that water waves are linear and dispersive. That means they're governed by a partial differential equation that is linear and tends to disperse initial conditions over time. Um, the so what he's seeing in the actual canal is a what he calls a great wave of translation, which is this big lump of water, this big mass of water that's just moving up the canal at like a constant speed, and it's maintaining its shape. And he chases it for like a mile and a half or something like that, and it keeps its shape until the canal starts to like wind and destroys the big mass of water. So he realizes, being a scientist of the time and knowing this behavior that everyone thinks water waves should exhibit is this dispersive behavior, he thinks this is very odd because this wave didn't disperse until we changed sort of the landscape that it was rolling through. So it turns out he tries to tell people about this anecdote, and nobody kind of believes him because everyone else thinks water waves, they got to be linear and dispersive. They're gonna deteriorate eventually. You couldn't have followed it for a full mile up the canal. So he decides to prove them wrong, and he builds this wave tank in his backyard, basically, uh, to try to generate more of these great waves of translation. And he does it, and that's what the report on waves is about. He studies these for a while, and he has some really good drawings of the channel and how to generate these waves. There's one way he does it where he like drops a mass into the water to displace a bunch of water, and it pushes up this big wave of translation that just travels down the wave tank. He does it another way where he like pushes the water with a big board, and it again generates uh, this big mass of water that travels at a constant speed until it hits the end of the tank. Um, and so he has all these great diagrams on it, and he also discovers that there's a relationship between the speed of the wave, the height of the wave, and the width of the wave. So it turns out that uh, the the smaller the wave is horizontally, the higher it is vertically, and the faster it travels down the tank. So he finds like this empirical relationship, and he publishes that in this work. And still, people don't really believe him until some mathematicians, a little while later in 1895, derive the form of this solution. And they call it a solitary wave because it's this solution to this fluid dynamical equation that just is this one lump wave that travels at a constant speed. And the kicker with this is that it's still true that if the wave amplitude is small enough, you can approximate it with a linear dispersive partial differential equation. But if the wave amplitude is a little bit larger than that, then you need to take into account nonlinear effects of the fluid dynamical equations that like govern the system. So this solitary wave is sort of a balance between the nonlinear effects and the linear dispersive effects in the partial differential equation that allow it to keep this profile and keep moving
So
along.
dispersive effects are trying to, let's say, elongate the wave, make
Yeah,
it disperse out.
right.
You mentioned nonlinear effects have the, let's say, opposite effect. So what kind of nonlinear effect is present in the solitary wave that is working against the dispersion?
Yeah, so the nonlinear effect, it's you can kind of think of it as this model problem for wave breaking. Like literally when you go to the beach and you watch the waves come in and they break. When the waves are coming towards you, what's happening is the side of if we start with a wave that's just kind of like a mound of water coming in from the deep ocean, the side that's the side on the front side of the wave begins to steepen, and the back side of the wave elongates a little bit until eventually it kind of crests and rolls over itself, right? So there's a model equation known as Invissid-Burger's equation, or the Hopf equation, that describes sort of this beginning of this wave breaking phenomenon. And there's a term in the equation that these people in 1895, known as Korteweg and de Vries, who derived this solution, they derived from the fluid dynamics equations, that has the nonlinear term from Inviscid-Burger's equation inside of the Korteweg-de Vries equation, which is what this equation eventually becomes called. And so the idea is that that nonlinear term is trying to steepen the leading edge, while the dispersive effect is trying to spread out the wave. And the competing effects sort of balance for the solitary wave and just allow it to propagate on at a constant speed.
Okay, so we'll come back to this KdV, as you call it, KdV equation. But before then, you also mentioned in your thesis that these solitary waves weren't observed until a later problem arose, including Enrico Fermi. So I'm interested in hearing what the story was there.
Yeah, so in 1953, a couple of people, Fermi, Pasta, Ulam, and a graduate student, Sing Yu, were working at the Los Alamos National Lab on a computer there that was recently built called the MANIAC mainframe. MANIAC is an acronym that I don't remember what it stands for, but it's pretty funny. And they have still at the Los Alamos like National Lab History Museum, they have some of the vacuum tubes from the original MANIAC computer that were the old version of like transistors that we now have in our computers. So those are pretty. I have a picture of myself in front of them, which is great. I cherish that photo. So what they were doing on this computer was they were simulating atoms in a lattice, and letting them vibrate and exchange energy between neighboring atoms, essentially. So they modeled the lattice as a bunch of masses with springs in between. And they let it be periodic. So think of it as being like a very large circle where if you look at any single section, it pretty much looks straight. So you have some masses with springs in between. And you let the masses vibrate and the springs will exchange energy between neighboring masses. So if you let the spring force be linear, Hooke's law, the solution to that situation is well known. And it is because it's linear, it also has this linear superposition principle where you can add solutions together and you get, again, like on a guitar string, you have harmonics of this system. But what they wanted to do was make the springs slightly nonlinear. They added a cubic term. So you have Hooke's law, which is a linear term in displacement between the two masses. And they added a little bit like a cubic times some small number to the spring force. And what they expected is that if you start it in one harmonic of vibration, where all the atoms are kind of moving together, eventually that nonlinear term should move energy between harmonics. And eventually you'd get what they call thermalization, where the energy is evenly spread out between all the harmonics. That's what they expected. And the motion just looks sort of random. And they were trying to show this because at the time it was like in statistical mechanics, this is the theoretical understanding, but it still hasn't been shown in any like rigorous context exactly how this energy thermalizes in a system. So they coded it up with the big punch cards and everything. And they simulated this system for a long period of time. And what they found was very surprising to them. They found that it didn't relax to energy being equally distributed between all the harmonics. Eventually, if you waited long enough, all of the energy would go back and it would form the original initial condition they started with. So they started with the energy all in the longest wavelength harmonic. And what would happen is you would see, if you look on the short time, energy would leak out of that harmonic into the other harmonics. But eventually, it would all recollect back into that one initial long wavelength initial condition. And not only that, but it was almost periodic. It was like the time period that it would happen with was like almost the same every time. So they were like really puzzled by this. What the heck is going on? It's a nonlinear system. They expected it just to thermalize and be done, right? So it took a couple more years until Zabusky and Kruskal solved this problem in 1965. They wrote a paper showing that the system of masses and springs, was actually a discretization of the KdV equation. So it's when you model a PDE on a computer can't handle a continuous function, so you have to do what's called discretizing, where you take values of the function at usually like equal time steps, and then you model the derivatives as differences in the function and everything like that. So what they found was that what they were modeling was a discretization of the KdV equation. And when they were able to model it a little bit better in 1965, they found that what was happening was this long wavelength initial condition. It would first steepen on one side, and right when it looked like the wave was about to break, it would actually get a little wiggly, and then you would see these solitary waves split off of the main initial condition. And then you'd see them rank ordered. So the fastest, tallest one would come out first, and then the next fastest, next tallest one would come out second, and so on and so forth. And because it had periodic boundary conditions, they would race around the track, and eventually the fastest one would catch up to the slowest one again, and they would all kind of collapse and come together and reform that initial condition in about periodic time. And so that was pretty surprising, even more surprising than the FPUT problem was originally, because everyone knows we just talked about how these solitary waves are solutions to the KdV equation. That doesn't seem surprising. But the fact that there are multiple of them in this solution is surprising, because this is a nonlinear partial differential equation. There is no linear superposition principle. So I can't just add together two solutions and expect to get another solution, because the nonlinear term messes this up, right?
But you're saying that if I have multiple solitary waves, solitons, as they're called, somehow I recover this linearity, or is it different?
There is sort of a way of thinking about this as being linear, but really what's happening is, if you think about the solitons, if they're far from each other, they're these like localized little humps, right? So if they're far from each other, then if I add those two together, the solution until they come near each other does look like the sum. But when they come and they're on top of each other, the solution is like nowhere near being the sum of the two. Then when they pass through each other, the fast one overtakes the slow one. What you actually see is that if you compare it to just the sum of the two moving at their own individual speeds, the fast one is a little bit shifted forward from where you expect it would be after the interaction. And the slow one is a little bit shifted backwards from where you expect it to be. So there's this memory of the interaction that makes this like a totally nonlinear interaction. But to your eye, it looks sort of linear at some points and at other points. And then in the middle, it's just like a total mess. Like you can't tell, oh, there's the little one, there's the big one. They're adding sort of coherently in the middle in some
So
way.
that's a really fascinating story of you call it the FPUT,
The
the
FPUT.
FPUT.
Yeah.
I want to go back to its relationship to the KdV equation. And I want you to try and tell us a bit more about this equation, because it does show up a lot in your research, and it kind of is the foundation of where you go afterwards. And I'm just curious, for the KdV equation, what kind of special properties does it have? And how does one attempt to solve an equation like this?
Yeah. So after they found this property that you could have multiple solitary waves in a KdV solution, they at the time, in the 60s, the QFT was taking off, and there were all these particles that people were talking about, and so they dubbed them solitons at that point. Solitary wave plus on. They look like particles in the solution, sort of, because they keep their identity through interactions and everything. So they called them solitons. And it was a few years later, in 1967, that Gardner, Green, Kruskal, and Muria were able to show that the KdV equation is what we now call an integrable equation, which means that it has infinitely many conserved quantities.
Integrable meaning infinitely many conserved quantities. Okay, so in physics, I learned that energy, for example, is conserved. Does that count as a conserved quantity?
Yeah, that's exactly one of these conserved quantities. So the original situation that you derive the KdV equation from is this fluid dynamical equation, right? So first off, you would expect physically that mass should be conserved, the mass of the water underneath the surface, right? So that is the first conserved quantity of the KdV equation is the total mass of water under the curve is conserved. The next one is related to the momentum of the particles of the water particles. If you add up all the momentums, that should also be conserved, right? That's the second quantity that you can derive as a conserved quantity of the KdV equation. The third one is related to the energy in the wave, right? The energy of the mass moving in the wave. That is the third conserved quantity. And then it turns out that there's an infinite number after that. Uh, there's just more and more quantities that you can calculate in the KdV equation that are conserved, just like those three we would expect physically to be conserved. There's infinitely more after that. And yeah,
It's a bit hard for me to conceptualize that I can have an infinite amount of conserved quantities. I mean, maybe I can say, okay, if momentum is mass times velocity, just take a simple example, and energy is mass times velocity squared, then is mass times velocity cubed and mass times velocity to the fourth, something like that conserved, or is it
it
completely different?
it is related to the if you look at the conserved quantities mass, momentum, energy, they are related to you can compute them through powers of the surface. So there are higher and higher powers involved, and they literally do go up. Like energy is related to the square of the surface, and you keep going up. There's cubes and fourths and everything like that, and all of those are conserved. So that's what the hierarchy really is. That infinite hierarchy of conserved quantities is related to powers of uh, the surface height, essentially,
So I have
which
an
has
infinite
information
amount of
about.
conserved quantities on the KdV equation. That usually tells me that it should be easy to solve. Is that true in this case?
Yeah. In this case, yes, it is easy to solve. So what they also demonstrated is that this infinite hierarchy of conserved quantities was related to the fact that this KdV equation is fundamentally related to the Schrodinger equation. The Schrodinger equation from quantum mechanics. So a completely classical system. This is what really got me interested in the beginning. A completely classical system that's describing water waves is somehow fundamentally tied to quantum mechanics, right?
Which is
And
waves of probability or something unrelated to water.
yeah. So if we want to talk about the Schrodinger equation real quick, it is an equation in quantum mechanics that describes the wave function, the evolution of the wave function, right? So the idea is in quantum mechanics, we have a particle, a quantum particle in a system, and what the system is a potential function as a function of space, right? So if we restrict ourselves to just one spatial variable, then at every point in space, you can say the system is exerting some potential energy on the particle or is giving the particle some specific amount of potential energy at any given point. And then we ask, what are the dynamics? This is the same thing in classical mechanics. You can ask the same thing. So if the Schrodinger equation says that if the energy of the particle, or first let's restrict ourselves to potentials that are they're defined over all of the real numbers. So it's like an infinite space potential function. But at infinity, it's going to be zero. So it's saying that there's nothing really going on at infinity. It's just empty space. But in the middle, we'll say the potential function dips a little bit. So if you think of this as like a roller coaster, then in the middle, you would kind of like, as you fall down one side, you would gain kinetic energy. And as you go back up the other side, you lose kinetic energy, right? So if we say there's a particle in there that has energy below zero, that means it has to be stuck somewhere in the middle because kinetic energy can never be negative, at least classically, right? So you'd have a particle oscillating in the middle. We'd call that a bound state. In the Schrodinger equation, when you solve for the wave function, you find that the wave function is localized near that area where the potential is below the energy, right? And then out towards infinity, it dies off very quickly. It's allowed to leak a little bit outside of there. That's what quantum tunneling is all about. But it dies off very quickly, and the probability that you'd find it out at infinity is exponentially small. So these bound states can only exist at certain energy levels, right? This is kind of the fun, like the thing that everyone hears when they first hear about quantum mechanics is these discrete energy levels, like in the atom.
So if I solve the Schrodinger equation for the simplest system of I trap the particle in a box of really high potential energy, then the solutions end up being discrete in energy. That's the classic example, or
Right.
I shouldn't
Yeah.
say classic to be confused with classical, but it's the number one
Quintessential.
example, the quintessential
Yeah.
example you see in a
Yeah.
quantum mechanics course is you get discretized energy levels by solving the Schrodinger equation.
Right. And if you wanted to solve specifically for the energy levels of the hydrogen atom, you would just make that potential function the Coulomb potential, right, of the center of the central positive nucleus, right? And then you'd be modeling what the electron is doing outside of the nucleus. That's exactly how it works in for the hydrogen atom. So you get these discrete energy levels. And then because if we're thinking about potentials that go to zero at infinity, if we ever have energy higher than zero, it represents a particle that can escape to infinity, right? Or you could think of it as a particle that's coming in from infinity with like a fixed amount of kinetic energy. It's got a fixed speed. And then it comes and it speeds up a little bit as it goes down the dip and then slows down as it goes up the other side and then it continues on, right? That's what would happen classically. In quantum mechanics, you solve the partial differential equation of Schrodinger's equation, and it tells you that you actually will have, if you have a particle that's coming in with probability 1 from, let's say, negative infinity in x, in the spatial dimension, there's probabilities that it will get transmitted through this potential or reflected through this potential back towards minus infinity.
So classically, I only go through basically
Right.
because
Yeah.
I have enough energy to go down and then back up. But in quantum
Right.
mechanics, there's a chance that I actually go backwards.
Yeah. There's just a quantum mechanical probability when you solve the equation, you find that there's always some probability that you'll reflect, you'll head backwards. So this is basically what you do with the Schrodinger equation is you do these mathematical quantum experiments where you set up solutions to the Schrodinger equation. You ask, what is the probability of reflection? What's the probability of transmission? And for a bound state, you're usually interested in what energy that bound state occurs at. And then another thing that you could derive is called the norming constant, which is related to, I like to think of it as being related to where like the particle is most likely to be. So it kind of tells you where the wave function is localized. It's information about where the particle is kind of sitting. So that's all the information that you can derive from the Schrodinger equation: reflection coefficient, transmission coefficient, eigenvalues, and norming constants. Eigenvalues are the energy levels. So it turns out that what Kruskal, Green, who was it? Gardner, Green, Kruskal, and Muria did in 1967 was they showed that if you take your initial condition to be a potential in the Schrodinger equation, or rather minus the initial condition, if you take the negative of your initial condition for the KdV equation and you make it the potential in the Schrodinger equation, the eigenvalues, as you evolve your initial condition under the KdV equation, the eigenvalues of the Schrodinger equation don't change, and the reflection coefficient and the norming constants change in a very simple way, an incredibly simple way. And then if you had some process to reconstruct the potential of the Schrodinger equation for different types of spectral data, the reflection coefficient, the eigenvalues, and the norming constants, then you would have a solution method for the KdV equation. Because you could start with your initial condition, negate it, find the eigenvalues under the Schrodinger equation and the reflection coefficient and the norming constants, and then evolve those under the simple time dynamics, and then reconstruct the potential and then renegate it at the end to get a solution to the KdV equation.
That is super interesting. So I want to solve a fluid dynamics problem. I say, I don't like to deal with fluids. Let me go to quantum mechanics. Okay.
Right. Yeah.
Quantum mechanics is going to be easier than fluid
Yeah,
dynamics.
so much easier because the time dynamics just happen to be easier when you solve that problem, that quantum mechanical scattering problem. Yeah.
Right. And then I do a bunch of quantum mechanics. I solve the Schrodinger equation. And you mentioned the spectral data, which are kind of, let's say, the data to describe your potential and the reflection and the transmission and the norming constant. And then I somehow go back to fluid dynamics with this
Right.
information in mind. And that helps me solve the problem. My
Yeah.
question is, first of all, that's super fascinating. You mentioned that the KdV is nonlinear. Somehow I go to the Schrodinger equation, which is linear, and then I can actually learn a lot of things that can help me solve a nonlinear equation, which is the
Yeah.
KdV. So how can I think of that? What's the magic there? How's that happening?
So it's exactly like if anyone is familiar with the process for solving a linear PDE, like you've already mentioned it, you sort of decompose your initial condition into these harmonics, right? And the harmonics have simple time dynamics. And then you sum them back up at the end to find the solution. It's exactly analogous to that. It is like you start with your initial condition, you conduct your scattering problem, you do the simple time dynamics, and then of the scattering data, and then you reconstruct under what's known as an inverse scattering problem, the potential at a later time. And that gives you your solution to the KdV equation.
Is this a common technique in solving partial differential equations, or is this particular to the KdV equation?
It's particular to the KdV equation and sort of its cousins in the nonlinear PDEs. These types of equations that have the infinite hierarchy of conserved quantities are rare overall in all possible nonlinear partial differential equations, but there are a lot of them still. So there's one called the nonlinear Schrodinger equation, which is interesting. It's interesting that it also has the Schrodinger equation. It's related to the Schrodinger equation. The Sine-Gordon equation is one that has this property. And then the other two equations that I'm most familiar with are the intermediate long wave equation, which is just a mouthful, and the Benjamin-Ono equation, which are sort of more direct cousins of the KdV equation because they also come from fluid dynamics, kind of a fluid dynamical situation.
I'm glad you brought those up. So those are more directly related to your actual research. So maybe we can dive into talking about the intermediate long wavelength equation, which we'll just call as ILW.
ILW, yeah.
Also is
intermediate
a mouthful.
Long wave, yeah.
And then the Benjamin Ono. So maybe we can start with the intermediate long wavelength. What is that?
Long wave.
Long wave
equation. Yeah.
Long wave.
Okay, so it's still a it's very similar to the KdV equation. It's the physical situation is at least very similar, but it's a fluid. You have a fluid setup where there's a ceiling and a floor, and there's a fluid in between, but it has a slightly different density below than it does above, and there's some interface that you usually refer to as a pycnocline, which is just a line where the density changes rapidly. So a good example of this would be like the ocean. The ocean has different layers that have different salt content, which changes the density slightly. And there are regions where the density sort of changes rapidly from one salt content to another. And that pycnocline in between is a surface. We think of it as a surface that if you modeled this in one dimension, in one spatial dimension, one time dimension, would be well governed by the ILW equation, but the requirement is that the oscillations of the surface have a small amplitude, so that we can do some approximations to the full fluid dynamics equations. The lower section of fluid has like a fixed depth, and relative to the wavelength of disturbances that you're interested in modeling, the top fluid is very shallow compared to that. So that's the situation that yields the intermediate long wavelength equation. Long wave. You got me saying it now.
I got you saying it now.
You got me saying it. The long wave equation. So the intermediate part is, the long wave part is that we're looking at wavelengths that are long compared to that top fluid depth.
You can see why I made that mistake.
Yeah, exactly. They are long wavelengths. Yeah, that's exactly right. But the intermediate part is that if you take that bottom depth, if you take that bottom depth to be very shallow too, you'll recover the KdV equation for the that would describe the oscillations of the surface of the picnic line in between the two fluids. And if you took that depth to be infinite, you would get what's known as the Benjamin-Ono equation, which is another integrable nonlinear partial differential equation.
So I have these three partial differential equations. We can take the ILW, which is sort of in between, let's say,
Yeah.
the KdV and then the Benjamin-Ono, and in certain limits, you recover one or the other.
Right.
And did your research focus on the ILW mostly, the Benjamin-Ono? Where do you take it from here?
Yeah, my research was mostly on the ILW equation. So the idea is you fix that depth, that bottom depth, and then you ask, what do solutions to the ILW equation look like? So it was already known as of the 70s that the ILW equation had an infinite number of conserved quantities and was integrable and had this same inverse scattering technique of solutions. But it's not mathematically, it wasn't as rigorous as the KdV equation. But the one thing that was rigorous about the intermediate long wave equation was the multi-soliton solution. So you can write down exactly what the solution is if you have a finite number of solitons, n of them, say. So what was done also in I believe the late 60s, maybe early 70s, was David Levermore and Peter Lax, who are my great grand advisor and my grand advisor, i.e., the advisor of my advisor and his advisor.
Got some academic genealogy over here.
Yeah, exactly. They worked out how if you start with a really broad initial condition to the KdV equation, you'll find that there are a lot of solitons in it. The solitons themselves are related to the eigenvalues of the Schrodinger equation. So this is known as the semi-classical problem in the Schrodinger equation. When an initial condition is a potential is very broad, there will be a lot of eigenvalues that sit inside of that potential, sort of. And what they found, what Lax and Levermore did, was they showed how the solution of these lots of solitons sort of coherently add in the beginning, and then how they break into the little solitons that come out afterwards.
The same thing that happened with the FPUT problem.
Yeah, what they showed, what Zabusky and Kruskal were looking at, numerically simulating on the computer. Lax and Levermore showed in a more rigorous mathematical way exactly how that works, and in particular, what the limit as the initial condition goes to infinity, what that solution looks like, and how to describe it. So I wanted to do that for the ILW equation, and because the n-soliton formula was known, I can sort of start by building out a very broad initial condition with a bunch of solitons in it, and then ask what happens as we evolve that solution under time, and see how the solitons break. So actually, I was only able to compute what that limit is before the solitons break in my thesis, to show rigorously that it does approach some specific profile solution to Inviscid-Burger's equation that I mentioned before. But I'm still currently trying to work out how it breaks and what governs the dynamics of the system after the fact. We still expect that it should be we should see each of the solitons in a little, generating this, what's known as a dispersive shock wave. But we aren't exactly sure what the math that describes it is.
So your dissertation went up to the breaking point where the solitons are expected to start flying off, let's say.
Yeah.
And now you're a postdoc and you're continuing this work. So what I'm curious about is, in the KdV case, or let's say the FPUT case, people did understand how those solitons emerge.
Right.
But why is it harder in the ILW case? Why is it that it doesn't follow, let's say, analogously how you would treat that regime?
Well, we do expect that it will follow analogously. the mathematics that govern the solution after that breaking in KDV, there it's well, I guess you'd say it's really high level mathematics. It has to do with algebraic varieties, hyperelliptic surfaces, stuff like that. There's a lot of interesting complex analysis that goes into it.
Are
Uh,
you trained on these things, or do you have to read up on your own and relearn some things,
uh,
or learn
the
some
the
things from
the
scratch?
algebraic varieties and the hyperelliptic surfaces, that was the thing that I was least prepared for, definitely going into my PhD. And yeah, I just had to like read about it a bunch and try to understand it. And now for KDV, I think I understand what's going on there pretty well. But the for ILW, there it's not known yet what the ILW version of those like algebraic varieties or hyperelliptic surfaces are. There's a couple papers that describe that attempt to describe what's going on there, but really I just haven't been able to parse it well enough to see exactly how I can construct my solution and show that the limit works in my for my the problem that I'm looking at with these many
So,
solitons.
work in progress.
Yeah, work
We're
in
getting
progress.
there.
Yeah.
Do you have any ideas? What do you hope to tackle in your postdoc aside from continuing the ILW work?
Yeah. So the right now I'm working on um, that problem that I was talking about with KDV. The uh, the solution that they found up until break time, they were able to show that that the solution approached a particular limit um, uh, with like pretty good errors. They knew what the error was between the limit that they were looking at and the actual solution, right? After break time, they didn't know what the error was, but they could still show that the limit approached it, that the solution approached the limit, but they didn't know what the error was essentially.
So
So
they
one
couldn't tell
problem,
you how fast, for example, or how accurate the solution gets
yeah,
closer and
yeah.
closer to.
If you're interested in knowing, like for this sort of a situation, this fluid dynamic situation, you're interested in knowing like exactly where those peaks are of the solitons, right? And that's kind of the information that they didn't have, is because these peaks, if you're a little bit offset from the peaks, you could be far from the actual solution there because it dips, stuff like that. So I've been working on generating with another postdoc here at UCF. I've been working on getting error estimates on this asymptotic limit that basically tells you kind of where those peaks are of the solitons coming out of the wave breaking. And then also there's a similar problem, a related problem for the nonlinear Schrodinger equation that I'm working on with the same postdoc and some professors here. So I've got my hands full with new projects too.
So, some viewers might be interested in trying to connect what you're doing to the more general case of fluid dynamics, which is the Navier-Stokes equations.
Yeah.
And perhaps one can ask, is there any relationship at all between KdV and ILW to the more general Navier-Stokes equations, or do those live in different realms?
Well, they are definitely related. Like these so the KdV and ILW equations are derived from Navier-Stokes, or really they're derived from, well, a simplification of Navier-Stokes, which is the incompressible Euler equations. Um, but it's in this very specific regime that these equations end up coming out. Um, the regime being you need small amplitude oscillations, you need long wavelength compared to some other physical dimensions in the problem, stuff like that. So they're very simplified equations from Navier-Stokes that come from Navier-Stokes. Uh, but the interesting thing is that the nonlinear term in Navier-Stokes is basically the exact same nonlinear term in these equations. So it's I don't know. It's still not really known exactly if these integrable properties exist in the Navier-Stokes equation or not. Um, but nobody's been able to find it yet. So that's the whole deal with the Navier-Stokes equation is that it's a more general equation, so it's a lot harder to solve, a lot harder to find solutions and everything. So that's kind of the deal.
So to end, I want to connect back to the idea of solitons. They come up as main characters in your research, and you said you were interested in this whole field when you realized there was a connection between fluid dynamics and quantum mechanics. So really your passion for physics was still there. It
Right.
didn't completely go away.
That's why they
So
gave me the physics PhD.
right. So is there any more connections between solitons and physics, perhaps in particle physics, quantum field theory? Where do solitons show up in physics aside from fluid dynamics?
Yeah. So when I first started this work, I still have a good relationship with my first advisor in Henrietta Elvang at University of Michigan. She was very supportive. She was extremely supportive in me finding my passion in physics and mathematics. So I was talking to her about why I was interested in this stuff, and she was like, "Oh, one of the first projects she worked on as a postdoc, I'm pretty sure, had to do with solitons in um, general relativity. So it turns out there are soliton-like solutions to the GR equations, the Einstein field equations, um, and they kind of represent black holes. Or there's different types of space times you can look at of different dimensionality, and they have like these black hole soliton solutions. Additionally, there's in string theory and quantum field theory, you get solitons, which solitons themselves are sort of these classical objects, right, from a classical equation that is just a lump in the solution or some localized thing in a solution, right? But you can find analogs of them in quantum field theory and in string theory where they're sort of a quantum version of themselves. So they're a soliton, but of indeterminate size and indeterminate speed, and they have these quantum properties to them. So people like to look at that. I think there's some cosmological kind of consequences of solitons with what's known as like domain boundaries and stuff like that from string theory. So people in higher energy physics and cosmology are sometimes interested in solitons too. I'm just kind of like interested in them in their classical sense, though. I don't want to get too deep.
Let's leave the quantum to a
Yeah, I'll do regular quantum mechanics any day, but the string theory stuff, I'll stay away from that.
later. All right. Matt, anything else you'd like to tell us today before we end?
um, Follow your dreams. I don't know. It helped me out.
It's always good to end on a
Yeah,
nice piece of advice for the listener. Well, Dr. Matthew Mitchell, thank you for joining us today.
yeah. Thank you for having me. I appreciate it.